Oh, good.
Perfect. We can see it now.
Perfect. Now we can see, right? Now we can see. So how to do full screen mode? Yeah. Is everything working now?
Yeah, perfect. Please go ahead.
Yeah, so I suppose it's good. And does everybody can see my cursor? The moving thing here? Yeah. Okay, yes. Perfect. So hello everybody. Let me reintroduce. Oh, I didn't do it. So let me introduce myself. I'm Tong from university. I'm previously a postdoc at the University of Massachusetts Amherst. Now I'm at University of Amsterdam, and double affiliated with University of Oregon. Thank you very much for the organizers, and it's such a wonderful conference, HEFT2021. I've been here for not being here, but virtually being here for a couple of days. Enjoyed lots of great and fantastic talks, and today I'm going to tell you a little story about custodial symmetry. Beyond the oblique. What does it mean? Going to reveal itself, later. It's a recent work last year. I done with my advisor Graham Cripps and Xiaochuan Lu, who also gave the streaming, whatever the functional matching method talk yesterday, and Adam Martin. Yes. So let's start. So let's go over what is the custodial symmetry. What do I mean? What am I talking about? Just a revision. The Higgs potential is invariant under it's Higgs is a complex doublet, right? SO4, the SU2 left, SU2 right, the old story. Go to SO, symmetry breaking, right? The VEV, SO3, and you have a remaining SU2. That is what we call custodial symmetry. Okay. And the folklore saying that custodial symmetry, UV theories that violate custodial symmetry are generally believed to be severely constrained. Say, for example, like the cutoff is like 10 TeV or larger by data from electroweak precision measurements, and that is folklore. Lots of people in our community believe that. And me and my collaborators, we are interested in the robustness of this result in the context of SMEFT. We want, so basically we want to ask the question: is BSM physics custodial symmetric? Well, the folklore believes it's like for custodial violation that must happen at least above 10 TeV or something. Is it true? So there's a question mark we do have. So if you have any questions, like at least for myself, if I have any questions, first place about particle physics, first place where am I going to go to? Yes, the PDG, right? So I go to the PDG. By the way, thanks for my collaborator Xiaochuan. I just steal his picture here. But anyway, so you see this ST plot, right? This ST plot. So what is it telling you? This ST plot on the PDG electroweak, chapter. It's telling you we have the S parameter as a T parameter, and in particular the T parameter is related to the custodial symmetry violation, right? The T parameter define alpha T, roughly the gauge boson 2-point functions. It's roughly 0. You see, it's pretty close to 0 in this small blob, and the value is pretty small. That's why custodial symmetry is heavily constrained, and the folklore believes that it's pretty high scale. And so it's from electroweak precision measurement from experiment. So what actually the experiment measurements do we do about the T parameter? The PD said it's the rho parameter. Yeah, of course. W mass over Z mass, the cosine, Weinberg angle. Yeah, it's 1 plus alpha T, and at tree level it's roughly 1. And this is telling you that standard model is, preserves custodial symmetry pretty well, pretty much. Okay, but the story I'm going to tell you today is that, well, this is not correct. I wouldn't say it's just wrong, but it's like at least naive and incorrect. So what's happened? Let's see. The custodial symmetry, almost like 30 years ago. Yeah, I believe this is almost 30 years ago in the original paper by Peskin and Takeuchi. they correctly point out that there are actually two different rows. Yeah. The row I just mentioned and PTG used, the W mass and Z mass, this is called the Veltman row. And the Veltman row, actually, this is all from Peskin and Takeuchi's original paper. Right? Rho is 1 plus this thing. You see, it has S parameter, the T parameter, and U parameter, which means that all of the three, S, T, and U, they all contribute to the rho parameter, not only T. So say rho is just 1 plus alpha T, that's too naive, right? That's too naive. That's just simplified things, oversimplified things. Okay, now then what does Peskin's original paper mean, right? They say the T parameter in their original paper is defined by another quantity. The quantity is called rho star 0. Rho star 0 is truly like 1 plus alpha T. But how is it defined? It's defined the charge current over the neutral current in the 0 means in the 0 moment limit. So you see, that's a different definition from this NW over MZ. That's called the Veltman rho. This rho star 0 is different quantity. So there's a two rows, a tail of two rows. Okay, let's see. So the electric weak precision parameters STU, proposed by Peskin and Takeuchi originally, they work, properly only under the oblique assumption. That's how they should be used properly. All the corrections from heavy new physics, they're in the gauge boson 2-point functions. The gauge boson 2-point functions. All your new physics, BSM physics are here, and that means, and these UV theories, they follow the oblique assumption. They're called the universal series. So which means if you want to try to apply S, T, and U, they're only applicable to the universal series with the oblique assumption. So how about non-universal series? Then they do not follow the oblique assumption. These non-universal series, they have vertex corrections from heavy new physics. So S, T, and U are incomplete and problematic if you apply them to try to constrain your models. By vertex correction, you gauge boson, right? Fermions, but there's a vertex correction. You have BSM physics here. Then it's non-oblique, and you cannot use universal series. And specifically, the rho star 0. Remember, that's how the T parameter originally was defined. So the rho star 0 is charge current over neutral current is no longer uniquely defined in a non-universal theory. It depends on the fermion species, in this current, in the neutral current. So like up and down, for example, up and down fermions, they have different, rho star zeros. Well, so everything, indicates that we need some new indicators instead of S and T. For example, let's look at a non-universal example. This UV Lagrangian has, some vector-like fermions. I have a vector-like fermions, and they have the Yukawa-ish, the Yukawa type, couplings. Okay, so I do the matching, at the leading order, onto SMEFT. But by the way, due to the time issue, I neglect all the introduction to what is SMEFT, because I think, as long as everybody's here in this conference, that's, obvious to everyone, right? What is SMEFT and what are the operators and Wilson coefficients. So I do the matching, the leading order, I got this operator. This is an operator in Walsall basis, from this Feynman diagram, you get this operator. This is a custodial violating operator. This operator violates custodial symmetry, which means this UV theory, this vector-like fermion with this kind of Lagrangian, UV Lagrangian, is custodial violating. But, however, you calculate the Peskin T parameter alpha T at 0 for this theory. So clearly we see a problem, right? That's for non-universal theories, T parameter fails. Oops. So now what to do, right? Let me tell you our approach toward this resolution. First, we try to carefully define custodial symmetry in the UV. Then we establish a custodial basis of standard model EFT at dimension 6. Then we map them onto observables at tree level. As a first step, we do tree level first, of course, right? then we find the correlations between them when custodial symmetry is imposed, which means the correlation between observables. Then, when custodial symmetry is imposed, let's see some pattern, find some pattern among these observables. Then we construct a generalization to the Pesquet T parameter. So, diagrammatically, you can see from this picture, right? Universal series is only a small subset of the all kind of the kaleidoscope of UV theories. And STU, when you matching them down to SMEFT, STU are applicable for universal series, but generally they're not. So what are we going to do? First, we define custodial symmetry in the UV. We define UV physics is custodially symmetric when there is a global SU2 right symmetry preserved in the limit G1 goes to 0. G1 is the G prime, the hypercharged coupling. G1 goes to 0 by all UV interactions with the Higgs sector of the Standard Model. So there are several merits in this definition. Clearly, we pondered it a while and came up with this definition for a reason. First, the breakings of custodial SU2 right by UV interactions, by this definition, we categorize them into two types. First, we call it soft breaking. The soft breaking will vanish in the limit G1 goes to 0. So if you take the hypercharge, coupling, gauge coupling G1 to 0, the soft violation vanishes. When the hard one, they persist. The hard ones, they persist in the limit G1 goes to 0. And our goal is to sniff out, to capture the hard custodial breaking, because the soft breakings are understandable, right? They're due to the gauging of hypercharge. They're two sources of custodial symmetry breaking in the Standard Model itself, right? First is the gauging of hypercharge. That's a gauging of hypercharge. And the second is the Yukawas, right? The Yukawas of uptime fermions and downtime fermions are different. They have a difference that breaks custodial symmetry, and the gauging of hypercharge. And the gauging of hypercharge is tolerated. So we think it's kind of course, it's persisted in the Standard Model, so no problem. So we are focusing on the hard breakings. So so we construct our custodial basis based on Walsall basis of dimension 6 SMEFT with the right-handed neutrino included. We add right-handed neutrino into it because for custodial symmetry, if you think about the lepton sector, right? Without a right-handed up-type lepton, that's kind of problematic. So we add them in and extend it so that such that in this way, the extended SMEFT, now it's actually new SMEFT, right? With right-handed neutrinos, is SU2 left cross SU2 right symmetry is manifest. Then we use the Higgs 2x2 2x2 sigma, the Higgs 2x2 matrix, right? By fundamental scalar, and that's the building block of our basis. So for example, there are I'm gonna here show two operators with hard custodial breaking. By the way, to capture hard breaking, you just see the tau3R, the T3, the tau3 generator. That's the smoking gun of custodial breaking in an operator. For example, the QHD in Walsall basis, turned into our custodial basis. We call it, the Wilson coefficient CHD goes to AHD, and this is the operator. You see the tau3R here, and the QHL1, that's the in Walsall basis. Now into our basis, it's this form, right? Sigma d sigma. You see the explicit T3R, the tau3R, is telling you that these two operators, as they have hard custodial breaking. So then here I'm gonna this table is lots of people here like you immediately recognize, right? This isn't the Walsall basis table. Well, it's pretty much the same, but now it's in our custodial basis. So the operators are changed into custodial basis operators. So these are based on Walsall basis. They include right-handed neutrinos. The red operators, the red color operators here are those with hard custodial breaking, and the purple, in the purple, purple rectangulars I circled out are the operators relevant to our study, because we do electroweak, precision, study on the custodial symmetry breaking. So these are the relevant operators, and among them, the red are the custodial breaking ones. So I said, we're gonna work, construct a new indicator based on observables. So these are our inputs, right? The standard input alpha, G Fermi, mz square, and these are the electroweak, precision observables, that we take. The end up usually they're called the LEP observables, the Z-pole observables, right? Z branching fractions to neutrinos, to electrons, right? Left and right-handed electrons, and W square, MW square, of course. These observables are predicted by the three inputs. Then we calculate them in the SMEFT at tree level, and then compare the prediction to the experiments. That's the scheme, right? You're gonna do. So how are they measured? Just a small reminder. Little reminder. Alpha is from electron G minus 2. G Fermi is muon lifetime. Z squared is from LEP, right? Mz Z mass, and the W mass, the most precise, the best measurement now is from LHC, no longer from LEP. And then we have the Z2 neutrino branching fractions. The branching fractions from Z2 neutrinos, right? How to do that? We use the total Z width minus the Z2LL, then minus Z2QQ, which are hadronic, the partial weights. We do subtraction, then say that and divided by 3 to get the Z2 neutrino, partial weights. ELL and this EE means right-handed electron and the left-handed electron. You can do the total, branching fractions Z2 electron and forward backwards asymmetry. Of course, these are. So
Hi,
then,
Tom, can I interrupt just a minute?
Yes.
Could you wrap up maybe in 5 to 6 minutes, because we were told if we don't finish this session soon enough, the local participant would not have any lunch left. So
I'm sorry, no problem. I'll try to be quick. Sorry.
Yeah, thanks a lot.
And by the way, so yeah, basically then we use Welterman rho instead of W squared and MW, and these are the expressions. These are the SMEFT corrections to these observables in our custodial basis. So then it's a simple observation, with simple algebraic, operations. You can find that the UV theories with custodial symmetries, which means that we remove all the red operators who they have hard custodial breakings in our table, and then if we remove them, we find a correlation. It's the rho, the Welterman rho, the Z partial weights to neutrinos, Z partial weights to electrons. They add up to 0. So if we added the red operators, hard custodial violating operators back, we got this one. It's the same linear combination of the observables. We'll give you this linear combination of the Wilson coefficients in our custodial basis. And then we define this thing to be script T. Script T is our new, generalized T parameter. The small little subscript of L means it's from leptons, from the lepton observables. So remember, this script T is an observable. It's an observable. But Wilson coefficients and ST and U's are not observables. Our script T is an observable. We construct, that's generalized. And it has the AHD, which is the CHD back in Warsaw basis, and AHL1, CHL1. The HD is from the oblique corrections, and this HL1 is from the vertex corrections. So first example, I'm gonna just screw quick. That's just a real triplet scalar. That's a very simple, UV theory. It's universal theory. So I'm just showing that it's custodial preserving. So the original T parameter, and our script T, they're the same. They're the same, So our T works equivalent to the original T for universal theories. Then let me go back to my previous example. That's the vector-like fermions. It's a non-universal. So the Peskin T parameter is 0 here, but we know it's a custodial violating, theory. Our script T successfully captured, the custodial violating here, And so it works with non-universal theories while the original T fails. And yeah, let me wrap up very quick. The constraint on this script T is dependent on the largest uncertainty, which is this Z partial width to electrons. Yeah. And so due to this larger uncertainty, so the bounds on the script T will be different than the ST plot in the PDG. And so let me summarize. The take-home message is that the ultimate rho is not an indicator of custodial violation. It actually receives contributions from S, which is custodial symmetric contribution. Peskin T works as an indicator only if the BSM physics is not oblique, it's a universal theory. We have generated T parameter into our script T, which finally in the Warsaw basis, this is, but remember this T is an observable, yeah, constructed from well-measured observables. At tree level, it captures custodial violation, both universal and non-universal theories. Thank you very much.
Thanks a lot. I'm really sorry about the cutoff.
Never mind.
Yeah, maybe just one quick question. Do we have anyone from the room? Okay. Please be quick. Brief.
I think it's a quick question. So is this all related to the fact that the operator OT, you can use equation motion, etc., to replace it by other linear combinations of other operators?
Which operator OT you mean? Is it the OT in the search basis or?
I mean, actually here, sorry, it's I think it's HD. Here,
yeah,
right? OHD,
the OHD is of course, yeah. Thank you very much for the question. It's a really good question. The OHD or the QHD, whatever, in the Warsaw basis, it is custodial violating. But there are other custodial violation in the contributions. For example, from vertex corrections, and the vertex corrections are in general, if the flavor, forget about the flavor universality flavor, different flavors can have different vertex corrections. Then the contributions from vertex corrections to the custodial symmetry, the violation is not captured by this OHD.
Okay, thanks.
All right, so if you have other questions, please ask on the Slack channel. I'm sorry, Tom.
I really apologize again, for everybody's lunch. So.
Not your fault. Okay, thanks a lot. So we will finish this session and see you in the afternoon.